So today we're moving on to chapter 6, where we're going to focus on solving first-order systems of differential equations. And the good news is everything we're going to learn about first-order systems applies to what we did back when we solved second-order ODEs. So for example, you can take any second-order ODE and write it as a system of first-order ODE. So here is a second-order differential equation. We're using the variable x as our unknown. We'll assume it's a function of time, t. And so the way we rewrite this as a system of differential equations is we make a substitution. It's our little trick for solving this problem. So we're just going to let y equal the derivative of x. So then we take the derivative of y, so that'll be the second derivative of x. And see, now that you compare these two, you're just going to solve the differential equation, the second order differential equation for x double prime. So we'll come down here and do that. So we rewrite our second order equation and we solve it for x double prime. We move minus 2x to the right hand side, minus 3x prime. Now, another trick here, notice x prime is the same thing as y. So we replace this x prime with y, and we replace x double prime with y prime. And that gives us the equation y prime equals minus 2x minus 3y. And that becomes the second equation in our system. So we now have the system of first order differential equations. The first equation comes from your assumption that y equals x prime. We've just rewritten it as x prime equals y. And then the second equation comes from solving this differential equation for x double prime and making the appropriate substitution. So we just put this equation there, and this is your system of differential equations. Notice they're first order. Your unknowns are x and y, and so when we solve this, we're going to be solving for x and y. Now, another thing we need to get used to is writing this system in terms of a matrix and vectors. And so we rewrite this component here as a vector made up of x prime and y prime. We look for the coefficients of x and y in each equation. The first equation doesn't have an x, so the coefficient of x is 0. Coefficient of y is 1. Coefficient of x here is negative 2. The coefficient of y is negative 3. And then you're just multiplying by the vector xy. So this is how we'll get used to representing a system of first order equations as x prime, where x is the vector xy, and then we just call this matrix A. So x prime equals ax. So this represents a system of first order ODEs. So let's verify that this is a solution to the system x prime equals ax, where A is this matrix, the one we just found for the previous system. Alright, so all we're going to do is substitute this solution into this system. So let's make sure that x prime, the derivative of this vector, is the same thing as multiplying that matrix times the vector. So how do we differentiate a vector? It just means we differentiate each component. So if we differentiate e to the minus 2t, we get e to the minus 2t times the derivative of minus 2t, which would be minus 2 e to the minus 2t. Same thing here. The derivative of e to the minus 2t will be minus 2 e to the minus 2t, multiplied by the negative 2, and you get 4 e to the minus 2t. So that's the derivative. Now what do we get when we multiply the matrix A times x? Well, we get 0 times e to the minus 2t plus 1 times negative 2 e to the minus 2t. That's what we have here. Minus 2 times e to the minus 2t minus 3 times negative 2 e to the minus 2t. That's what we have here. This just gives us negative 2 e to the minus 2t. This gives us minus 2, and then a plus 6. When we add these two together, we get 4 e to the minus 2t. So notice, this and this are the same. So this is a solution to the system. We'll be turning that around in the future. We'll be given a system and we'll find the solution. But for now, we're just trying to verify. So in general, how do we solve a first order system? X prime equals AX. Well, just like we did with first order and second order, we assume a solution has a certain form. Here we assume our solution looks like v, a vector, times e to the lambda t power. Well, this lambda is called an eigenvalue of the matrix A, and v is the corresponding eigenvector. And I'll explain those a little bit more now. So what are eigenvalues and eigenvectors? So let's let A be a square matrix. That just means it's n by n, like 2 by 2. That's going to be our main focus here. The number lambda is called an eigenvalue of A. If there is a non-zero vector v called an eigenvector, so that the matrix A times v equals the number lambda times v. So that's what it means to be an eigenvalue and an eigenvector. So let's just run through a quick example. Let's show that lambda equals -2 and v, given by the vector 1, -2, is an eigenvalue eigenvector pair of this given matrix. And again, this is the same matrix we saw in the very first example we did. All right, so let's calculate A times v. When we do that, here's our matrix A, here's our vector v. So 0 times 1 plus 1 times -2. -2 times 1 plus -3 times -2. Add these things up. This gives us -2. This gives us -2 plus 6. We simplify to -2, 4. And what do we get when we calculate lambda times v? So lambda times v gives us -2 times the vector v. That just gives us -2 times 1. And then -2 times -2, which gives us 4. These two things are equal. So we verified that this is an eigenvalue eigenvector pair. Again, we're doing verifications now. Eventually we'll be finding the eigenvalues and the eigenvectors. That's what we get to do next time. Now, why do we care about systems of differential equations? Well, there are lots of applications. So depending on what your major is, you might encounter some of these over time. This is one of my favorite ones, the predator-prey model. So here, your X represents the size of the prey population. You might think of that as like rabbits. Y represents the size of the predator population. You might think of that as the foxes. And this is a mathematical model which describes their population sizes and how they change. So when you see an X times a Y, that's like an interaction between a predator and a prey. These numbers A, B, C, and D are all positive numbers. So if you have an interaction between a predator and a prey, it hurts. You subtract. The rate will be subtracted by that interaction. So an interaction hurts the prey population. It's added. It adds to the predator population. So it's just sort of an interesting thing. You can also do the spread of diseases like the coronavirus we're looking at now. All the data they're gathering and the predictions are based on differential equations. For you electrical engineers and mechanical engineers, you study spring mass systems and LRC circuits. If you look in chapter 7, you'll see here's a LRC circuit described as a first order linear differential equation. This problem up here is nonlinear. We won't learn how to solve that one this semester, but we will learn how to solve this linear system. So you'll know how to do lots of applications in your whatever major you're studying. So that's why they're important. That's why we study them.